In an earlier video, you might remember noting that when looking at the shortest path from a given source to a given destination, if we focus on a prefix of that shortest path, let's say from the source up to a certain vertex, let's call that x, we had seen that this prefix of the shortest path from the source to the destination is itself optimal, which means this red oval also represents the shortest path from the source to that vertex x. And to build the shortest path from the source to the destination, we had to start from the shortest paths from the source to longer and longer prefixes, building on those subproblems in order to build the entire shortest path from the source to the destination. We wouldn't get the shortest path from the source to the destination in one shot. We would have to rely on the solutions to those smaller subproblems, knowing that the optimal solution to those smaller subproblems can be built upon to construct the optimal solution to the overall problem. So this property of optimal substructure was extremely important when we designed the greedy algorithm, which we called as Dijkstra's algorithm. So let us ask the question as to whether optimal substructure applies to this current problem that we are facing, where we also have a constraint that we can't use more than k plus 1 edges. So we know that this gray path is the shortest path from the source to the destination, which uses less than or equal to 6 edges as per the constraints of the given problem. The question is, if we look at any prefix of that path, let's say we take this prefix from the source up to x within the blue oval, is this blue prefix the shortest path from the source to x, which uses less than or equal to 6 edges? So let me ask this question: is this the shortest path from the source to x which uses less than or equal to 6 edges? Well, the answer is clearly no, because we know that the shortest path from the source to x which uses less than or equal to 6 edges is actually this other path composed of these green arrows. So this means that we don't have optimal substructure in the presence of this constraint, in the sense that if we have an optimal path from the source to the destination satisfying the constraint, and if we take a prefix of that optimal path, that prefix is not necessarily optimal in that same way, right? We just saw here that this blue oval does not depict the shortest path from the source to x satisfying that same constraint that you're not supposed to use more than 6 edges. So because there is no optimal substructure in that sense, we can't assume that the shortest path from the source to the destination satisfying the constraint can be built out by using the solutions to smaller subproblems corresponding to prefixes of the original problem. And the graph we have here illustrates that perfectly. The shortest path from the source to x satisfying the given constraint is composed of the green edges. The shortest path from the source to the destination satisfying the same constraints is given by the gray edges. So you can't build the gray path by taking the green path and extending it by 1 edge. It is a completely independent path. And this is why Dijkstra's algorithm failed us in computing the shortest path distance from the source to the destination satisfying the given constraints. Even though it was able to compute the answer correctly up to x, it could not compute the answer correctly up to the destination because this property of optimal substructure was lacking. So because it's lacking, you cannot extend the solutions to smaller subproblems to construct solutions to larger problems which might be totally independent of the solutions to those smaller subproblems. But this doesn't mean we can't make progress, because it turns out that there is optimal substructure in a slightly different sense. And let me explain what I mean. When we look at the shortest path from the source to the destination, which uses less than or equal to 6 edges, that's the gray path we have drawn. If we look at the blue prefix of that gray path from the source up to x, we can say that this prefix does represent the shortest path from the source to x, which uses less than or equal to 5 edges. So it's not the shortest path from the source to x that uses less than or equal to 6 edges, but it's definitely the shortest path from the source to x which uses less than or equal to 5 edges. If you look at the green path uses 6 edges. So if we had to find the shortest path from the source to x which uses less than or equal to 5 edges, it would actually be the gray path. It wouldn't be the green path. So when defining subproblems, when looking at prefixes of the original problem, if we can reduce the number of edges allowed for those smaller subproblems, for those prefix subproblems, then we might end up with optimal substructure. For example, if what we have here is the shortest path from the source to the destination which uses less than or equal to k plus 1 edges, which is what we were given in the original problem, then the red prefix represents the shortest path from the source to x, using less than or equal to k edges. If we write this as k plus 1, it would not be correct, but if we write this as less than or equal to k edges, it would be correct. Why is that? Because suppose there was a shorter path from the source to x which used less than or equal to k edges. Right, so suppose from the source to x there was a shorter path which used only a few edges, and we have an edge from x to the destination. Then what we could have done is we could have followed that shorter path to go to x and then taken that lone edge from x to the destination to get a shorter path overall from the source to the destination which uses less than or equal to k plus 1 edges. But that contradicts our original assumption that we are already looking at the shortest path from the source to the destination which uses less than or equal to k plus 1 edges. So this means the prefix, the red prefix, must be the shortest path from the source to x which uses less than or equal to k edges. So if I call this value as, let's say, f of destination comma k plus 1, then this value can be written as f of x comma k. Right, let's say f of destination comma k plus 1 is the shortest path up to that destination which uses less than or equal to k plus 1 edges. And here we are assuming that the source is a global source, so I'm not putting it as a parameter within f. This f reflects the length of the shortest path from that global source to x, which uses less than or equal to k edges. Why have I put k as a second parameter? Because only when we reduce that value of the second parameter do we get optimal substructure. If we didn't have that as a second parameter, if I just had f of destination and f of x, I know that if this f of destination is the length of the shortest path from the global source to that destination, which uses less than or equal to k plus 1 edges, then this must be the length of the shortest path from the source to x, which uses less than or equal to k plus 1 edges. And we know there is no optimal substructure if we define our functions in this way. But if we allow that k plus 1 to be reduced for the prefix subproblems, then we have to indicate that reduced value for the number of hops by putting the number of hops as the second parameter. And we prefer to do that because doing that introduces optimal substructure. The property of optimal substructure is important if you want to build a greedy algorithm or a dynamic programming algorithm. So in general, we want to say that our function f of, let's say, v comma I, where v is some vertex and I is an upper bound on the number of hops, this is the length of the shortest path. This is the shortest path length from the global source, so the global source doesn't change here, to this vertex v using less than or equal to I hops or edges. So how do we calculate the value of f of v comma I for different values of v and I? Our goal is to find the value of f of destination comma k plus 1. This is the value that we are interested in calculating. But because of optimal substructure, this value will have to be constructed from the values for smaller subproblems. So for example, let's say this is our vertex v, and let's say it had 3 incoming edges from 3 neighbors. Let's say those neighbors are v1, v2 and v3. Let's say these edge weights were w1, w2 and w3. So if I had to express f of v comma I in terms of smaller subproblems, how would I do that? Well, I would look at the fact that any shortest path from the source leading up to this vertex v using less than or equal to I edges would either have to come into v from here, from v1, or from v2, or from v3. It has to be one of those 3. If the shortest path came from v1, then what would be the length, what would be the value of f of v comma I? It would be f of v1 comma I minus 1 plus w1. Why is that? Because this value is the length of the shortest path from the source to v1 using less than or equal to I minus 1 edges. And to that cost I add the cost of the final edge from v1 to v. Similarly, if the shortest path from the source to v, let's say, had come in through the second edge from v2, In that case, f of v comma I could be written as f of v2 comma I minus 1 plus w2. And if the shortest path had come in using the third edge, then the total cost of that path would have been f of v3 comma I minus 1 plus w3. Now I don't know which of these three is going to be exactly equal to f of v comma I. But if I knew those three values, if I knew these three values, I could compute these three sums and then I could pick the minimum among them and claim that f of v comma I must be equal to the minimum among them. So I'm sort of using the lazy manager's analogy here. As a lazy manager, if I was given the task of computing this value for the overall problem asks me to compute the value of f of destination comma k plus 1. Now I don't know how to get this value. Using the lazy manager's analogy, I am saying the shortest path from the source up to this destination will be some sequence of edges. I don't know what that sequence of edges is, but I am going to focus only on the very last edge in that shortest path. What options do I have for that last edge? Well, maybe when I look at the destination, maybe it had 4 incoming edges from 4 different vertices. In that case, I'm going to call 4 subordinates and give them the task of solving this problem, the problem of computing the shortest path from the source to each of these 4 vertices using less than or equal to k edges, not k plus 1 edges, but k edges. If I could have these 4 values. And how will I get those 4 values? Well, I will call 4 subordinates under me and give them the task of calculating each of those 4 values respectively. So those 4 people come back and tell me those 4 values. I'll take the first value, add this weight w1 to it and see what the sum is. I'll take the second value, add the weight w2 to it and see what the sum is. I'll take the third value, add w3 to it, and the fourth value and add w4 to it, and I'll compare those 4 sums. And I know that the shortest path up to the destination, which uses less than or equal to k plus 1 edges, must be the minimum of those 4 sums. So I don't have to worry about how those subordinates calculated those values. I am focused only on the last step using the lazy manager's analogy. And in fact, those subordinates themselves would be using this same strategy. They would also want to be lazy. They would also want to focus only on the last edge for their respective subproblems, and they will try to hire some other people under them to solve the smaller the subproblems that are even smaller than their subproblem, in order to build up the solution to their subproblems. So a general worker in this imaginary corporate hierarchy would be trying to calculate the value of f of v comma I for some vertex v and some integer I. And how is that worker going to calculate the value of f of v comma I? Well, the worker will check who are the predecessors of v in the graph, in the given directed graph. Suppose x is a predecessor. In that case, the worker will call someone under them to calculate the value of f of x comma I minus 1. right? If the worker has to calculate the shortest path length from the source to V using less than or equal to I hops, then their subordinate has to calculate the value of f of x comma I minus 1, right? X is the predecessor of V. So if this is V, X is any predecessor of V. We know that the shortest path from the source to X can use at most I minus 1 edges if we plan to extend that shortest path up to V by adding that last edge. So if we know this value, then we could add the weight of the final edge from X to V. Let's say that's W of X comma V. By taking this sum, we would have one possible way to get the value of f of V comma I, but of course there could be many different predecessors of V. So we would have to actually take the minimum of this value over all the predecessors of V. So we have to take this value, the min of this value for all predecessors x of V. So x here denotes an arbitrary predecessor of V in the graph. So compute this sum for each of those predecessors and then take.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today